This is M. Prasad Raju, stand before you to continue the classes of Unit 4 of Engineering Mechanics for first years. The topic belongs to this is area moment of inertia of composite figures. In the previous video lecture, we have completed area moment of inertia with respect to simple figures and what is polar inertia, what is product of inertia, what is perpendicular axis is theorem is telling, and etc. topics we have discussed. Now, in this video lecture, we would like to do the problems on the three major topics like area moment of inertia of composite figures and area moment of inertia of shaded regions. Now, if you look at this particular problem, as it is the first problem based on area moment of inertia of composite figures, the problem is as shown in like this. Determine the moment of inertia of following figure about centroidal YY axis. If suppose, for example, if in the examination, if you have given problem like this, our ultimate article is to find out the area of the given composite figure. Before we are going to do that, whether it is simple figure or composite figure or shaded region, the first duty we have to do it for is applying the symmetric property. That means if we apply the property of symmetry to the given diagram, then the diagram will split up into the 2 or 3 parts, we can conclude. That means, if you apply, if you look at this problem, in this problem, we are asked to find the moment of inertia of the composite figure. And if you look at this problem, this composite figure is consisting 3 different types of specimens. What are they? If you look at this, if you apply the symmetric property to this diagram, what we can understand is, this given composite figure is not symmetric to any of the axes. That means we need to find both x-axis and y-axis for the determination of centroid of this given composite figure. So the first duty is we have to apply the symmetry property to this. Okay, let us apply. If we apply the symmetry property to this, we can conclude one point to this particular diagram. What is that? The given composite figure is not symmetric to any of the axes. Then we need to find both x coordinate and y coordinate. Now, the second duty is the splitting of this given composite figure. That means how many of the different specimens that are involved in this diagram. If you look at this diagram, in this diagram, I am going to split this into 3 categories of the specimens. The first category is semicircle, the second category is rectangle, third category is triangle. Now, first of all, we have to find the areas of semicircle, area of rectangle, area of triangle. And for the determination of the areas of these 3 different specimens, we need the measurements, and that using these measurements, we are going to find the areas of the 3 different specimens respectively, semicircle, rectangle and triangle. Let us see this. The solution of this particular composite figure is as follows. The solution of this problem is divided into 3 parts. The given composite figure is classified into 3 parts, namely part 1 is semicircle, part 2 is rectangle, part 3 is triangle. Now, how to find the areas of these 3 different specimens? If we will see the first one, part 1 is semicircle. The area of semicircle is denoted by A1, that is equal to, we have a stipulated formula. What is that? Pi r square by 2. We know that area of a circle is pi r square, and if you want to find the area of semicircle, A1 is equal to pi r square by 2. That implies A1 is equal to pi into 2.5 whole square by 2. What is this 2.5? This 2.5 is radius given in the problem, that is considered as radius of the semicircle. Therefore, A1 is equal to pi into 2.5 whole square by 2. After simplifying this, as pi carries 3.14, we will get A1 is equal to 9.81 centimeter square. Similarly, next we need to find both x coordinate and y coordinate. Let us see the first coordinate x1. x1 is equal to r minus 4r by 3 pi. This is a formula to find out the x coordinate when we have given with respect to the semicircle. Therefore, x1 is equal to r minus 4r by 3 pi. After substituting the value of r in place of 2.5 and after simplifying, we will get x1 is equal to 1.44 centimeter. Similarly, coming to the part 2, this is called rectangle. In the part 2 of rectangle, the formula for area A2 is equal to L into B. And if you look at the second portion of the given composite figure, My L carry is 16.5 and P carry is 5 centimeters. And after simplifying this L into B, we will get A2 is equal to 82.5 centimeter square. This is called area of the rectangle. And we need to find the x2 coordinate and y2 coordinate relevant to this second part, that is rectangle. How to do this? X2 is equal to L plus L by 2. This is a formula to find out the second coordinate belongs to a specimen of rectangle. Therefore, x2 is equal to L plus L by 2, that is equal to 2.5 plus 16.5 by 2. I already told you in the previous unit that is determination of centroids due to simple figures, composite figures and shaded regions. The formula is same for all of them. What is that you know? If we want to find the second x coordinates, we need to find we need to move from left hand side to right hand side direction. But finding y coordinates, we need to move from lower direction to upward direction. That we have to remember. Therefore, x2 is equal to L plus L by 2, that is equal to 2.5 plus 16.5 by 2. And after simplifying this, we will get 10.75 centimeters. This 10.75 centimeters is nothing but what here? The second coordinate denoted by x2 of the specimen rectangle. Coming to the third part, the third part of this given composite figure is called triangle, and the area of triangle is A3 is equal to 1 by 2 BH. In the formula, A3 is equal to 1 by 2 BH, my B is called breadth and H is called height. And if you segregate only the triangle portion of the specimen among the three of the specimens in a given composite figure, and we got only the measurements related to its breadth and height, that is equal to 1 by 2 into 8.5 into 4. If you simplify 2 in 4 two times, after simplifying this, I will get my A3 is equal to 17 centimeter square. Therefore, now we need to find the x coordinate belongs to this third specimen, that is x3 is equal to L plus L by 2. And in this problem, this 2.5 belongs to the first specimen. This L belongs to the 8 belongs to the second specimen rectangle. And this third L represents the present parameter which is called triangle. So we need to substitute like that. 2.5 plus 8 plus in this particular case L, my L is nothing but called breadth here, that is 8.5. And if you divide it with 8.5 by 2 and adding to this 8 and 2.5, and after simplifying the whole simplification, which is equal to x3 is equal to 14.75 centimeters. This is what is known as the third x coordinate with respect to the third specimen, namely triangle. Now, we need to find in the three specimens, we find areas and x coordinates. Now, we need to find y1 belongs to semicircle, y2 belongs to rectangle, y3 belongs to triangle. That we will see now. Now, we need to find y coordinates belongs to first part semicircle, second part rectangle, third part triangle. Let us see this. y1 is equal to r. That means, as we know that first part is semicircle, my y1 is nothing but radius of the given semicircle. That is equal to how much? 2.5 centimeters. If you look at the diagram, the radius of semicircle is nothing but 2.5 centimeters. Therefore, we consider that itself is the y1 coordinate. Now, the utilization of x1 coordinate and y1 coordinate, we will find a1 x1 like this. As we have already find out a1, that is pi r square by 2. Bring the value of a1 and x1, we find a1 x1, that is equal to 14.12 centimeter cube. And utilization of y1 and a1, we can find a1 y1, which is equal to 24.52 centimeter cube. These two are, this a1 x1 and this a1 y1 belongs to the first part, that is semicircle. Similarly, go to the second part as it is called rectangle. My y2 is equal to b plus b by 2. As we don't have, as I already told you that to find the y coordinates, we move from downward direction to upward direction. This b is nothing but 0 because we don't have the previous portion. That is why b is considered as 0. And the second b representing rectangle breadth, that is 5 centimeters. Therefore, y2 is equal to 0 plus 5 by 2. That implies, after simplifying 5 with 2, we will get 2.5 centimeters. Now, utilization of the previous x2 and a2, we find a2 x2. That a2 x2 is equal to 886.87 centimeter cube. And utilization of y2, we find a2 y2, that is a2 y2 is equal to 206.25 centimeter cube after simplifying. This a2 x2 and a2 y2 is belonging to the second portion called rectangle. Similarly, coming to the third part denoted by triangle, in this triangle, we need to find y coordinate, that is y3 is equal to 5 plus h by 3. Here my h is representing height, therefore 5 plus 4 by 3, and after simplifying, suppose if we simplify 4 with 3, we got 1.33, and adding 1.33 to this 5, we will get how much? 6.33 centimeters. Therefore, now utilization y3 and a3, we find a3 y3, and utilization of x3 and a3, we find a3 x3, that is equal to 250.75 centimeter cube, and a3 y3 is equal to 107.61 centimeter cube. Now, using this a1 x1, a2 x2, a3 x3, we find x bar, and using a1 y1, a2 y2, and a3 y3, we find y bar. Now, we need to find to find centroid, we need two major coordinates, x bar and y bar. As we told that C of x bar comma y bar, now we are going to find out, that we will see now. Now, using a1 x1, a2 x2, a3 x3, we will find x bar. We have a specific formula for this. X bar is equal to a1 x1 plus a2 x2 plus a3 x3 whole by a1 plus a2 plus a3, that is equal to, bring all the values of a1 x1, a2 x2, a3 x3 and substitute in their respective places. We will get 14.12 plus 886.87 plus 250.75 whole divided by 9.81 plus 82.5 plus 17, and after simplifying this, we will get 10.5 centimeters. This 10.5 centimeters is considered as x bar coordinate, and similarly, bring a1 y1 for the first specimen, and a2 y2 from rectangle, a3 y3 from triangle, and bring all the values and substitute in the respective values. We will get y bar is equal to a1 y1 plus a2 y2 plus a3 y3 by a1 plus a2 plus a3. Then why we are going to add all of them? Because we have given the composite figure. As I already told you that determination of area moment of inertia with respect to three categories. What are they? The first category is simple figures. The second category is composite figures. The third category is shaded regions. Okay. So, for finding y bar is equal to a1 y1 plus a2 y2 plus a3 y3 whole by a1 plus a2 plus a3, and bring all the values of a1 y1, a2 y2, a3 y3 and substitute in their respective places. We will get 24.52 plus 206.25 plus 107.61 whole divided by, as a1 is 9.81 plus a2 is 8.5 plus a3 is 17, and simplifying this, we will get 3.09 centimeters. Now, after getting this 10.5 centimeters is considered as x bar and 3.09 centimeters is considered as y bar. Now, we need to find the first duty is centroid of the given composite figure is given by centroid C of x bar comma y bar is equal to C of 10.5 comma 3.09 centimeters. This is the first portion of determination of centroid. Whenever we ask to find area of moment of inertia of about a centroidal y-y axis, our ultimate article is to find AMI of the centroidal y-y axis. That means we need to find I double y. That means, let us see, that is the second portion of determination. When you are going to find out AMI of any composite figure, the first primary action is to find centroid of this, and the second portion is determination of area moment of inertia. The problem is not completed. Strictly understood that the centroid, first of all, we have to find centroid, and by the utilization of centroid, then we are going to find out area moment of inertia of the composite figure. That we will see now. Now, we need to find moment of inertia of given section about the given y-y axis. Similarly, determination of IYY. IYY means moment of inertia with respect to centroidal y-y axis. That is the meaning of determination of I double y. Now, I would like to find this I double y. We divide this particular composite figure into three parts. Part 1, as we know, that semicircle. Part 2, as we know, that rectangle. Part 3, as we know, that triangle. Now, if you take part 1, the formula for determination of I1 double y is equal to I1 double y is equal to Iy1 plus A1 d1 x square. Therefore, Iy1 is equal to, we have a stipulated formula to find out the moment of inertia of centroidal y-y axis with respect to a specimen of semicircle is this formula. What is that? 0.11 r to the power of 4. And in the semicircle, our radius is 2.5. Therefore, 0.11 into 2.5 to the power of 4. After simplifying this, we will get Iy1 is equal to 4.296 centimeter to the power of 4. Similarly, coming to the second part, which is called rectangle, the moment of inertia with respect to the rectangle, we have a formula, that is I2 double y is equal to Iy2 plus A2 d2x square. This is the formula. Now, in this formula, Iy2 can be determined by using a stipulated formula, that Iy2 is equal to 1 by 12 L cube B. Okay. Now, bring the value of L and substitute B, we will get 1 by 12 into 16.5 whole cube into 5. The 16.5 is belonging to the length of the second portion, which is called rectangle, and 5 is called what? Breadth of the second portion. What is that? Rectangle. Therefore, after simplifying this, we will get y2 is equal to 1871.7 centimeter to the power of 4. Now, coming to the part 3, as we are calling it as triangle, the formula to find I3 double y is equal to Iy3y3 plus A3d3x square. Okay. Now, again from this Iy3y3 is equal to 1 by 48 into hb cube. This is a stipulated formula. As I told you in the beginning, we have determination of moment of inertia for the 6 specimens. As I told you in the beginning, that the first one is rectangle, the second one is triangle, the third one is right angle triangle, the fourth one is circle, fifth one is semicircle, sixth one is quarter circle, etc. like that. So, we have stipulated formulas of determination of moment of inertia with respect to centroidal x axis and centroidal y axis. So, in this particular composite given figure, we are asked to find AMI due to centroidal y axis. That is why we are finding I double y. Therefore, y3 is equal to 1 by 48 hb cube. Bring the value of height of the triangle and the breadth of base of the triangle. Substitute in these respective values. We will get 1 by 48 into 4 into 8.5 whole cube. And after simplifying this, we will get Iy3 is equal to 51.177 centimeter to the power of 4. Now, in the 3 specimens, my dear students, we have completed Iy1y1, Iy2y2, Iy3y3. And the rest of the terms A1 d1x square from this portion, A2 d2x square from this portion, A3 d3x square from this portion. That we will see now. Now, we need to find d1x for the specimen of semicircle, d2x for the specimen of rectangle, d3x for the specimen of triangle. Let us see this. d1x is equal to x bar minus x1, that is equal to 10.5 minus 1.44, and after simplifying this, we will get 9.06 centimeters. Similarly, a1 d1x square, that is equal to 805.24 centimeter to the power of 4. Now, utilization of a1 d1x square plus Iy1, we will get I1yy is equal to 809.536 centimeter to the power of 4. This is the ultimate moment of inertia with respect to centroidal y axis of the first specimen semicircle. And similarly, for the second specimen rectangle, d2x is equal to x2 minus x bar, that is equal to 10.75 minus 10.5, that is equal to 0.25 centimeter. Now, A2 d2x square is equal to 5.156 centimeter to the power of 4. Similarly, here also, utilization of Iy2y2 and A2 d2x square, adding both of them, we will get I2 double y is equal to 1876.85 centimeter to the power of 4. Now, coming to the part 3, d3x is equal to x3 minus x bar, that is equal to 14.75 minus 10.5, which is equal to 4.25 centimeters, and A3 d3x square is equal to 307.062 centimeter to the power of 4. Therefore, I3 double y is equal to 358.24 centimeter to the power of 4. Now, utilization of I1 double y, I2 double y, I3 double y, we need to find determination of I double y. Let us see that one. Now, our ultimate article is to find out determination of I double y, and to determine this I double y, we need I1 double y, I2 double y, I3 double y. Now, substitute 3 of them. Now, the moment of inertia of a given composite figure with respect to the centroidal y axis is given by I double y is equal to I1 double y plus I2 double y plus I3 double y. Strictly speaking, that when you are going to calculate I double y, we must be in a conscious that this I1 double y belongs to semicircle, I2 double y belongs to rectangle, I3 double y belongs to triangle. Because in the given composite figure, we have 3 parameters. We have 3 specimens. What are they? The first one is belonging to semicircle. The second one is belonging to rectangle. The third one is belonging to triangle. Now, the total moment of inertia with respect to the centroidal YY axis, which is denoted by I is equal to I1 plus I2 plus I3 bring all the three values with respect to the three specimens and substitute in the respective places, we will get I is equal to 809.56 plus 1876.85 plus 358.24. After adding three of them, we will get I is equal to 3044.62 centimeter to the power of 4. This is the ultimate answer, which is called moment of inertia with respect to centroidal YY axis. This is the way to find the solution of moment of inertia of a given problem, as we asked to determine the moment of inertia of the following figure about centroidal YY axis. This is the methodology, which is a very important method of finding the moment of inertia with respect to a composite figure. This is the final answer, that is I is equal to 3044.62 centimeter to the power of 4. In the previous video lecture, we have completed determination of area moment of inertia of simple figures. In this video lecture, I would like to deal two methods. One is determination of moment of inertia of a composite figure, and the second one is determination of area moment of inertia of shaded regions. Now I will do the second method. Now we are coming to the problem number 2, that is determine the moment of inertia of the following shaded region about centroidal XX axis. So our ultimate article is to find out I towards this diagram. First of all, we will split this diagram into the two parameters. That means before we are going to do that, as I told you in the previous problem, that if you have given any problem like this, first of all, we will apply the property of symmetry. Let us apply the property of symmetry to this diagram. If you apply symmetry property to this diagram, strictly speaking, that the given figure is not symmetric to any of the axes, and we need to find both the x-axis and the y-axis. For that reason, by giving these measurements, we will split this diagram into the two portions. The first portion is rectangle, the second portion is quarter circle. Now we need to find the area of the two of the specimens, area of a rectangle and area of a quarter circle, that we will see now. The given section is divided into two parts. First part is rectangle, second part is quarter circle. How to do this problem? The first part is rectangle. To find area, we have a standard formula A1 is equal to L into B, that is equal to 30 into 20, which is equal to 600 centimeter square. And the coordinate of x1 is equal to L by 2, that is equal to, my length is 30. Finding area in this first parameter, that is x1 is equal to L by 2, that is equal to 30 by 2, which is equal to 15 centimeters. Y1 is equal to B by 2, that is equal to 20 by 2, that is equal to 10 centimeters. And utilization of x1 and A1, we find A1 x1, that is equal to 600 into 15 is equal to 9000 centimeter cube. Utilization of y1 and A1, we find A1 y1, that is equal to 600 into 10, which is equal to 6000 centimeter cube. Similarly, for part 2, that is quarter circle, we have a stipulated formula for finding area of quarter circle, that A2 is equal to pi r square by 4, which is equal to 3.14 into 5 whole square divided by 4, which is equal to 19.625 centimeters square. Similarly, for finding x2 coordinate, x2 is equal to 30 minus 4r by 3 pi, that is equal to 27.877 centimeter, and y2 is equal to 20 minus 4r by 3 pi, that is equal to 17.877 centimeters. Now, utilization of A2 x2, we find A2 x2. We utilization of y2 and A2, we find A2 y2. Bring both of them and substitute in the formula of x bar. Let us see this. Now, we need to find the x bar coordinate by the utilization of A1 x1 and A2 x2. But in this particular formula, the shaded region is consisting of positive region and the remaining portion is negative region. That is why we will substitute A2 x2 portion belonging to quarter circle that was subtracted from the shaded region of rectangle, that is x bar is equal to A1 x1 minus A2 x2 whole by A1 minus A2, and bring all the values of A1 x1, A2 x2 and A1 A2 in this formula. We will get the 14.564 centimeters. And similarly, y bar is equal to A1 y1 minus A2 y2 by A1 minus A2, that is equal to 6000 minus 19.625 into 17.877 by 600 minus 19.625, which is equal to 9.734 centimeters. Now, utilization of x bar and y bar, we need to write the centroid of the given shaded region, that is now centroid C of x bar comma y bar is equal to C of 14.564 comma 9.734 centimeters. Now we need to find the moment of inertia of this given shaded region with respect to centroidal x-axis axis that we will see now. Now, to find the moment of inertia of a given section with respect to x-axis axis, again we are going to split this into two parts. I XX is equal to I1XX plus I2XX. In part 1 we will find I1XX and we have a stipulated formula. What is that? I1XX is equal to Ix1x1 plus A1D1y square. Ix1x1 is equal to, again we have a formula, 1 by 12 LB cube, bring the value of L and B, substitute here, we will get 20,000 centimeter to the power of 4. And D1y is equal to Y1 minus Y bar. For the first coordinate, we find Y1 minus Y coordinate. We will subtract Y coordinate from Y1. That is equal to how much? 10 minus 9.73, which is equal to 0.266. Now, we using this Ix1x1 and A1D1y, we will get I1XX is equal to 20,000 plus 600 into 0.266. After simplifying this, we will get I1XX is equal to 20,042.45 centimeter to the power 4. Similarly, we are going to find I2XX for the second part. What is the name of the second part here? Quarter circle. I2XX is equal to Ix2x2 plus A2D2y square. Therefore, Ix2x2 is equal to 0.055 r to the power of 4. That is equal to, after simplifying this, as we know that radius is 5, we will get 37.375 centimeter to the power of 4. Similarly, D2y is equal to Y2 minus Y bar, which is equal to 17 minus 877 minus 9.734, which is equal to 8.143 centimeters. And after simplifying this total, you will get I2XX is equal to 34.375 plus 19.625 into 8 into 1.143 whole square. We will get I2XX is equal to 1335.678 centimeter to the power of 4. Now, utilization of this I2XX and I1XX, we find I XX. Bring both of them and adding in this formula, we will get I XX is equal to I1XX plus I2XX. That we will see now. To find the moment of inertia of a given section with respect to x axis, we know that I1XX is the moment of inertia of the portion of rectangle and I2XX is the moment of inertia of the portion of quarter circle. But quarter circle is not in shaded, but rectangle is in shaded. Therefore, what is the specimen which does not shaded is going to be subtracted from the moment of inertia of the shaded specimen. That is, I XX is equal to I1XX minus I2XX. Strictly speaking, that, my dear students, here we have to understood that I1XX is the moment of inertia with respect to shaded specimen, that is what, rectangle. And we are subtracting the moment of inertia of quarter circle, that is denoted by I2XX. Bring both of them and we will get I XX is equal to 20,042.45 minus 1335.678. We will get I XX is equal to 18,706.772 centimeter to the power of 4 is considered as the moment of inertia of the following shaded region with respect to centroidal x-axis axis. In the given problem, whenever we looked at the problem, are we asked to find the moment of inertia with respect to centroidal x-axis axis or centroidal y-y axis? If we asked with respect to x-axis axis, we find only I XX. If we asked to find y-y axis, we find only I-Y-Y. If we asked both centroidal x-axis and y-y axis, then we need to find both I XX and I-Y. But in this particular problem, we are asked to find only the moment of inertia of the following shaded region about centroidal x-axis axis. Hence, we have find that I XX is equal to 18,706.772 centimeter to the power of 4. So, we have completed the determination of area moment of inertia with respect to the three categories. The first category is determination of area moment of inertia of simple figures that we have completed in the previous video lecture. And in the present video lecture, we completed two problems related to the determination of area moment of inertia of a composite figure, that is problem number 1, and determination of area moment of inertia of a given shaded region with respect to centroidal x-axis axis is the second method, that is shaded regions. Therefore, three types of specimens with methods we have. What are they? I told you very clearly that determination of area moment of inertia of simple figures, determination of area moment of inertia of composite figures that we have completed in this present video lecture, and determination of area moment of inertia of the shaded region. This is what is known as the third category. And with this, we have completed the determination of area moment of inertia with respect to three categories. determination of area moment of inertia of simple figures, composite figures, and shaded regions. The remaining part will be continued in the next video lecture. Thank you very much.